Okay, let's get started. Good morning. Okay, let's try that again. Good morning. Good, thank you. Okay, so we're going to be looking at section 3.6. Building upon implicit differentiation and chain rule, and now we can look at the derivatives of logarithmic functions. We'll look at a simple kind of log. Y is equal to the natural log of x. Just like we focus on e to the x, the natural exponential function, and we look at a to the x when a is not e, we'll focus on natural log, and then we'll take a brief look at what happens when the base is not e. And as usual, we're concerned in finding if y is natural log of x, what is the derivative of y? Okay, using implicit differentiation, we can find this very, very easily. Remember, y is equal to natural log of x is equivalent to the expression e to the x is equal to, e to the y is equal to x. Sorry about that. Let me rewrite that. That's bad. E to the y is equal to x. We're still concerned in we're still wanting to find the y prime, right? Derivative of y. But now we know chain rule, we can handle e to anything. We know implicit differentiation. We can handle when y is defined implicitly. We can find this pretty quickly. Let's take the derivative of this on both sides. Derivative of e to the y with respect to x, of course, is the derivative of x with respect to x. Left-hand side, we have e to the something. Derivative is e to the same thing multiplied by derivative of that something. In this case, it's y. Right-hand side is just a 1. We want to know y prime, and we're almost there. Y prime is equal to 1 over e to the y. And like how we handled inverse trig functions, we're not going to be very happy with the derivative in terms of y. We want this in terms of x. So we can go back to this line right here. Okay, replacing that with an x, and here we go, we got an x. So what this is telling us is that the derivative of the natural log of x, after we've gone through all of that, turns out to be just 1 over x. For what values of x is that expression valid? What can x not be? 0, what else? Negative, right. So we need to specify that x is this is only valid if x is strictly positive, right? 0 obviously is a problem. Negative is going to cause a problem in the natural log. Okay, so that's a very simple expression right here. Derivative of natural log of x is 1 over x. Derivative of log of any other base is more complicated. We'll look at that case at the end of the class today. We'll focus on just the natural log for the majority of today. Let's first look at some simple examples, and then we'll look at a few examples where we can use properties of log to vastly simplify what we have to do. But again, simple stuff first. By the way, let me add a little bit to this. Every time we learn a basic derivative, remember, we also know the chain rule version of that. Derivative of ln of x is 1 over x. Derivative of ln of u, where u is something other than just an x, is 1 over u times the correction factor du dx to account for the fact that u is something more than just an x. Okay, so again, every basic derivative you know and will learn can all be modified this way for the cases when you have to use chain rule. All right, back to this example. This one's not so bad. We know how to take care of tangent of u, right? So derivative is simply secant squared of u, whatever you want u to be. In this case, natural log of x is a very good choice for u, times du dx, derivative of ln of x. So there's our dy du, secant squared of u times du dx. And we know what this is equal to now. Once again, be very careful. Secant square of this thing, this is one quantity. This 1 over x cannot be moved into here. That does not belong to the secant square. That's an entirely separate quantity. So to avoid confusion, you may want to write it this way, just to make it clear that 1 over x has nothing to do with the ln of x. That's part of secant. Let's swap these things around. Let's say we have natural log of the tangent of x. So for this one, we'll just use the modified basic rule for natural log. This is the chain rule version of this. We have natural log of u, where u is something more than just an x. And the chain rule tells us, first we get 1 over whatever we're calling u, in this case tangent, 1 over u times derivative of u. And derivative of tangent is secant squared. Just the basic chain rule. And as you know, with every trig expression, there are other ways to express exactly the same thing, sometimes in slightly simpler way. So let's take a look at what's going on here. 1 over tangent is the same as 1 over sine over cosine. And secant squared is the same as 1 over cosine squared. So we could simplify this a little bit. Notice one of these cosine factors can cancel. And in the end, we get 1 over sine times 1 factor of cosine. Again, on WebAssign would take that. No complaints whatsoever. It would also take that. Now, as when you deal with this kind of thing, it depends on what you're doing next. If you're looking for one more derivative after this, maybe this is an easier thing to deal with compared to secant square and tangent. It all depends on what you are doing, finding the derivative for. Okay, let's do one more basic example, and then we'll look at the more complicated stuff. X to the 8th over natural log of x. The obvious thing to do here is simply use the quotient rule, and there's nothing wrong with that. There's nothing really you can do to simplify this anymore, so, quotient rule, we'll see where it takes us. Quotient rule says we take the denominator times derivative of the top, 8x to the 7th, minus the top, derivative of the bottom. Natural log of x is 1 over x. All divided by whatever is downstairs squared. And that's about it. Other than simplifying just a little bit, there's not much left to do. The only thing really left to do here is to take out the x to the 7th, but even that really doesn't do much. And once again, on WebAssign, they would take this very happily. But just make sure you can do simple simplification in case something like this shows up on the exam. Okay, any question on any of these simpler stuff we just did? Okay, now we're going to look at more complicated stuff where there's a hard way to do each of these, and there's a smarter way to do each of these. Y is equal to the natural log of x to the 3rd times the 5th root of cosine of x squared. Natural log of x cubed times 5th root of cosine of x squared. Okay, let's first look at the obvious way someone might handle this thing and see what kind of complications we will run into. So the more obvious way, turns out to be the harder way, is if we let this be natural log of u, where u is equal to this pretty ugly looking thing. Then we know dy dx is simply dy du, du dx. This part is not hard. That's just 1 over u, right? Because y is ln of u, so dy du is 1 over u. Now it's this, that's going to be a problem. Derivative of this is, you can use the product rule and then with chain rule all over the place. It's not impossible to do, but that's going to be something that slows you down. Okay? So nothing really wrong here. It's just that it's a pretty cumbersome thing to handle right here. I'll just say it's not easy to do. So here's a little smarter way. You got to remember that with natural log of products, for example, we can split into simpler logs. Let me rewrite this thing right here. That can be looked at as natural log of x cubed times this some other thing. This thing turns out to be cosine of x squared of to the power of 1 over 5. Now we're going to use the property natural log of a times b is natural log of a plus natural log of b. All right, so here I'm going to let a be x cubed. So this can be split into natural log of x cubed plus natural log of that other thing. The function has not changed. We haven't even taken derivative yet. However, you can see that we split one complicated log into two simpler logs. And there's more that can be done here. Remember, we can use another property, natural log of a to the power of b equal to b times natural log of a. And those, by the way, work for any base. It doesn't have to be natural log, but we're doing natural log here. So I can further move these powers to the front. So this can be written as 3 natural log of x plus 1 over 5 natural log of this. Okay, so see what happened here. We went from one complicated log to two much simpler log. This one, in fact, is as simple as it gets. This one's a little bit complicated, but not by too much. Not so bad. Can I move that 2 to the front? Why not? Right. It belongs to x, which belongs to cosine. So the cosine of that's one thing. That's just one quantity. You cannot move that 2 out. Now, if the 2 were next to the cosine, then that means cosine of x, the whole thing squared. Then you can move that 2. But in this case, that 2 belongs to x, which is part of that cosine. So that 2 cannot be moved. That 2 has to stay. Okay? Now we can take the derivative. Y prime 3 times derivative of ln of x, simple, 1 over x, right? Plus 1 over 5 times derivative of natural log of u, we've done that before, 1 over u times the derivative of u. U here is cosine x squared. So derivative would be negative sine of x squared. Right? Is that it? What am I missing? 2x. Right. Derivative of 2x. Derivative of x squared, 2x. Very good. What's the 2x doing here? Why is there a 2x? Why is there a 2x there? Exactly. When we took the derivative of this part, 1 over u, u is this thing right here, du dx involves another chain rule. It's another cosine of u, du dx, right? It's what we did last time when we had chain rule within a chain rule. So that's the from chain rule within a chain rule. Okay, so it looks pretty complicated, but the good thing is essentially this is done. You can simplify a little bit, but other than that, there's really not much left. 3 over x plus, well, minus, sorry, right? Minus, what do we want to do? About 2x sine of x squared over 5 cosine x squared. Or 3 over x minus 2 over 5x. And this is really tangent of x squared. Okay, so there it is. Okay, once again, with WebAssign, simplification is not a big deal. Don't worry. Don't spend too much time on that if you don't want to. It will take it. But however, you should know at least the basic things that you would have to do to simplify, especially trig expressions. There's always a way to make an existing trig expression simpler, and there are lots of ways to make an existing trig expression more complicated. Okay, any question on this example? Okay, so the idea here is you always want to simplify a complicated log expression. Log of big nasty thing, break it into smaller, easier to handle pieces. That's always better than dealing with log of a complicated thing. This is hard. This is much easier than that. Okay, now we're going to look at a technique called logarithmic differentiation. That's also another trick with logs that you can do to simplify complicated stuff. And I'll do this by an example. That's a 4. We've seen something very similar maybe a week ago when we did chain rule within a product rule. You can use product rule first times derivative of the second, where you got to use chain rule, and then reverse the thing, and then chain rule again. So that's one option. Okay, not terribly difficult, but it takes a little bit of work, a little bit of time. Now the other option is to use this thing called logarithmic differentiation. The way this works is you start out by taking log on both sides. So y is equal to this whole thing. That means ln of y is equal to ln of that entire thing. Now we can do to the right side what we did on the last example. We'll break a complicated log into many smaller and simpler logs. So let's simplify this one here. For starters, we see a product, so let's break that into 2. That can be written as ln of the first thing plus ln of the second thing. And then you see these powers here. Remember, we can move those powers again. That's always the idea here. Always simplify the log expression as much as you could. It's much easier to deal with many but simpler logs as opposed to one but complicated one. Just break it into simpler stuff as much as you can. Let's take that 3 to the front. Left-hand side all this time is still ln of y. Okay, so that's as far as we could do with the natural log stuff. You cannot break this up anymore. You cannot break up natural log of the sum of 2 things. You can break up natural log of a product of 2 things, but not the sum. Not the sum or difference. You can break up quotient and product, but not sum or difference. This is it. There's nothing more you can do to simplify any further. Now remember, we're still looking for y prime. And now we have y implicitly defined as opposed to explicitly like we had originally. Let's differentiate this implicitly to find y prime. Left-hand side, ln of whatever is 1 over that whatever times, now we got to account for that, this y is something to do with x. We may or may not know what it is. It doesn't matter. The chain rule says we have to multiply by derivative of that. And once again, left-hand side is ln of u. U is y, so it's 1 over u times du dx, dy dx. Right-hand side, 3 times ln of something. It's 3 times 1 over that something times the derivative of that something, 4x cubed. Now the second one here, 6 times ln of something. 6 doesn't do anything. ln of blah is 1 over blah, d blah. There we go. Okay, so notice that instead of doing product rule and chain rule, all I did was using simple derivatives of natural log with chain rule. But that's not hard. Let's simplify the right-hand side just a little bit before we deal with that y. So what do we get? We get 12x cubed over x to the 4th plus 2 plus 30x to the... Oh, what did I do? 4. Yoink. All right, that's it. Okay, so there it is. Okay, so y prime times y prime divided by y is equal to this thing here. If I just want y prime, I just multiply the y to the right-hand side. So we get y prime is equal to y times that entire thing And once again, every time you take the derivative of something, you want your answer to be in terms of x, just x. if possible. If you have y here, find a way to get rid of it if possible. Okay, so what is y really equal to? If you look all the way to the top of the last page, that's the definition of y. So let's simply change that to y, which is x to the 4th plus 2 to the power of 3 times x to the 5th plus 1 to the power of 6 times all of that stuff. And that's good enough here. Of course, you can multiply this in here to further simplify. If you multiply this into the first term, that will cancel out one factor of this. So you have this square times this to the 6 times that stuff, plus that times this times that to the 5th. You can do that, but this is good enough. All right, does that make sense? The idea of logarithmic differentiation. Any question on this example? Okay, let me give you one example for you to try on your own for a few minutes. Same idea along the same line here. Y is equal to the cube root of x to the 6 plus 2 over x minus 2. Okay, let me give you 2 minutes. Give it a shot. You can do this without logarithmic differentiation, but please do this with log differentiation. All right, so that's 2 minutes. Okay. So let's see how we can handle this. First thing I would do is to rewrite that cube root. I'll give the power 1 over 3 to the entire thing. Now when you take the log, natural log on both sides, you can immediately make that 1/3 power irrelevant by moving it to the front. So this is equivalent to 1/3 ln of that thing. Now we can split that complicated log into simpler stuff. Product is addition, quotient is a difference. So this is 1/3 times this entire thing, natural log of the top, minus natural log of the bottom. And be very careful that 1/3 gets applied to both of these. Both of these gets that 1/3, not just the first one. It's up to you what you want to do with that 1/3. You can distribute it now, or let's distribute that. Okay, don't forget, left-hand side, all this time is still natural log of y. Right-hand side can be written as 1/3 natural log of x to the 6 plus 2 minus 1/3 natural log of x minus 1. Yeah. I'm sorry? The first step on the last page. Where? Oh, this one. Yeah, I messed up. Sorry. That's a 2, sorry. Could have changed that to 1 and changed, never mind. It's good. Okay, it should remain the same. You never change those things. Okay, now you take the derivative on both sides. Left-hand side, 1/y, y prime. Right-hand side, two simple logs, 1/3 times 1/x to the 6 plus 2 times 6x to the 5th minus 1/3 times 1/x minus 2 times derivative of x minus 2 is 1. Minor simplification, 2x to the 5th, x to the 6 plus 2 minus 1/3x minus 6. So I brought this 3 down here and multiplied it in. And now y prime is equal to y times that whole thing. And then you just have to look up what y was all the way back, that thing with a cube root. There's my y times all of that stuff. And there we go. Of course, you can simplify this and rearrange a few things here and there, but that should be the answer. Okay, how many people got very similar stuff? Good, good, wonderful. If you didn't get there, please find out where you got stuck. Okay? With log differentiation, you can handle all sorts of really strange-looking things. For example, y is equal to, let's say, x to the power of x. Okay, so that's a very, very strange looking function. You got a variable x to the same power, right? Now the usual power rule we know, you bring the power down, reduce power by 1. That only works if the power is a constant. In this case, the power is not a constant. The power happens to be a variable. So that exponent that's changing, that's really causing a bit of an issue. Well, we know how to get it out of there. If you can get it out of the exponent, everything is going to be fine. So that's where logarithmic differentiation is useful again. Log allows us to move that exponent however we want, use it as an exponent or a coefficient. So we have ln of y is equal to ln of x to the power of x. Natural log allows us to move this x to the front. And now the right-hand side is a very simple thing. It's just this basic product rule. We got two functions of x. X is easy. Natural log of x is easy. So let's take the derivative on both sides. Left side is 1 over y, y prime. Right-hand side, using the product rule, we get first times the derivative of the second plus the second times derivative of the first. That's a 1. So I don't have to write that 1 there. And so product rule on the right. Simplify, this is a 1. Now it's easy. Y prime is equal to y times all of that stuff. But I know what y is equal to. It's really that thing. And there we go. That's the derivative of x to the power of x. Okay, so every time you got any kind of complicated power that you don't want to deal with, consider using log differentiation. Any question on this example? All right, so now let's take a look at what happens when we have log to some other base and not just the natural log. We'll leave it very general. Let's say y is log base a of x. We'd like to find out the derivative for that. And everything rests upon implicit differentiation again. Okay? The equivalent statement to this is a to the y is equal to x. Differentiate implicitly. Left-hand side, right-hand side. Okay, who remembers the derivative of a to the something? And? What important rule are you missing? Yes, chain rule, chain rule. Always the chain rule, right. If it's just an x, then you're right, you stop there. But it's more than just an x. So remember, we're going to use the basic rule that we saw maybe once before, I think. It's a to the x times ln of a. And then every basic rule you know can be modified for the case when that x gets replaced to something, becomes something more complicated. Left-hand side is a to the y times ln of a times derivative of that y to account for the fact that y is not just an x. And right-hand side, of course, is a 1. So, modify just a little bit. 1 over a to the y times ln of a. And as usual, if you can get rid of y on the right-hand side, you should always do so. A to the y, look up here. From that statement, the equivalent statement is a to the y is x. So this guy is simply x. So this is just ln of a times x downstairs. Okay, so that's the derivative of ln log base a of x. 1 over ln of a x. And notice that if a is equal to e, then derivative of ln log base e of x is 1 over ln of e x equal to 1 over x, as we expected. Right? We know log base, natural log of x has derivative of 1 over x. So that statement is true for any valid base of a, including e itself. All right? Questions? All right, then that's it for today. See you Friday. Oh, by the way, I've instructed the TAs to return the exams in recitation tomorrow. Tomorrow you'll get your exam booklet back. Okay? That there is a quiz. Yeah, you just get your exam back. There is a quiz.